My name's Simon, and this talk is about visualizing software architecture using something I created called the C4 model. For those of you who don't know me, I've written a bunch of books in the past, mostly related to either software architecture or Java. You can find these things online. As you can tell from my accent, I'm not local. I actually live in a small island called Jersey. Can you see it? Not really, it's kind of too small, isn't it? So if this was interactive, we could do the pinch to zoom in thing, and Jersey gets a bit bigger. There it is now. Still kind of small. We pinch to zoom in one more time. There we go. There's Jersey. So it's a small island off the coast of France, 9 miles by 5, population 100,000 people. It's British, not English. It's all very complicated, is the short answer. Why do I live there? Basically, I was born there, lived there as a kid, moved to the UK where I worked in London for about 12 years for consulting companies. So my background is predominantly working for consulting companies, building software, mostly in Java. Moved back to Jersey in 2008 with my family, did some .NET stuff, and now I'm doing things like this, which is quite fun. So onto the topic. One of the things I get to do is I get to fly around the world, and I get to talk to teams about software architecture. And specifically, one of the things I do with these teams is I run architecture carters with them. So basically, here are some requirements, break up into groups of 2-3 people, go away for like 90 minutes, do some design, and draw some pictures to somehow visualize your design. So a nice, simple exercise. Now, everybody can do the design part. So designing software is actually the easy part of this exercise. The complicated part is actually drawing the pictures to describe your ideas and your solutions. So I've been running this exercise for about 10 years now, and I've got 15 gigabytes of photos at home that look like this, or that, or that. My personal favorite. This is like an airline route map. This is this green blob's like London Heathrow. Like, lots of routes around the world. It's just crazy different boxes and styles and all sorts of things. Or this one. This represents all of your software systems. Look, business logic as a box in the center. Doesn't really tell you anything at all. This one here is typically what people call a logical architecture diagram, and this is basically just words from the requirement specifications with boxes and lines between them. This one here has no technologies. This one here is just a bunch of C# things floating around a database for some weird reason. I don't think this is a microservices architecture. I think this is something very, very different, but that's not apparent from this picture. Like this one. This is one of those choose your adventure books. So you kind of choose your own path through the diagram. No matter which path you take, you die and end up in the trap. All paths lead to the trap. This is describing a much more kind of complex, event-driven, asynchronous style of architecture. And the thing I like about this is that the calculation engine is adding 2 numbers. Like, that's it. It's a microservices architecture for adding 2 numbers. One of the things I like to see on diagrams are little people. So then we can see how human users interact with our system boundary. But we need to give them a name, otherwise it's just faceless clones like stormtroopers attacking, in this case, this ball reporting service. So yeah, I want to know what these people are and particularly what they're doing with my systems. This is why whiteboards are useful. So look, we don't need this thing here, we'll scrub it out. We don't need this line up here. Oops, sorry, yes we do, we put it back in. And we always joke that naming is hard, don't we? So look, there's some renaming up here. There's another one. That's not actually an architecture diagram, that's just a bunch of scribbles I saw in Central Park a couple of weeks ago, but it looks like the others, right? There's nothing too dissimilar here. And, again, this is a real diagram from a real workshop I ran. Now, this diagram, I think, started out as an entity relationship diagram. There's a crow's foot symbol in the top corner here. And this box in the middle, I think, was important because it was placed in the middle. And then this group scrubbed it out, and now the diagram is basically meaningless, and this was their feedback. Not super constructive. So we don't use tooling during this workshop. It's all pen and paper, pen and whiteboards. Now, of course, all these drawings are hand-drawn drawings. So you might be thinking, well, what happens if we use a tool? Well, that doesn't help. So if you go to Google and you ask it what it thinks a software architecture diagram looks like, you basically get this. Just page after page after page of essentially very pretty, colorful Visio-style diagrams. But they exhibit all of the same problems that we see with the hand-drawn pictures. So whenever I go and visit organizations and they let me look at their wikis or their documentation, I see diagrams like this. Do these look familiar to you? Yeah, because I stole them from your companies. No, I didn't. But these exhibit exactly the same problems. We've got different colored boxes here. We've got boxes without lines. We've got acronyms. We've got boxes of different sizes. So the whole thing is basically just a mess. What's the point of all this? The point of all this is essentially good communication. So lots and lots of teams are now trying to be agile and be lean and move fast and deliver stuff very, very quickly. In order to do that, as a team, as a collective, you need to be heading in the same direction. So this is essentially about creating good communication with each on team boundaries. So I asked the people who go through my workshop, did you find this challenging? And they say, yeah, we didn't find the design part challenging. It was the drawing pictures part that was challenging. And they often say things like, well, we're not really sure what types of diagrams we should be drawing, what notations we should be using, what level of detail we should be describing our systems to, and so on and so on. So there's a lot of ambiguity and questions out there around this topic. And basically, everybody struggles with this. So I've run this exercise now for about 10,000 people plus around the world in kind of 30 different countries. And pretty much every team I work with struggles with this exercise. And that's surprising, isn't it? It's surprising because as an industry, we've built all these fantastically huge distributed systems. We've sent people to the moon and maybe to Mars in the future, but we can't draw pictures of the things we're designing. It's just nuts. So you might be thinking, well, where's UML fit into all this? Who here uses UML? Quick show of hands. It's like 1.5. And again, that doesn't surprise me anymore. So when I first started asking this question, it was around the same sort of percentage, it's kind of like 10%. I'm now seeing many more teams where literally nobody on the team has even seen or been exposed to UML before. And there's an interesting generational thing here. So I graduated from university in '96. Literally the first training course I went on as a consultant was a select enterprise training course. It was like a 5-day modeling course. And so lots of the projects I worked on for the next sort of 5-10 years, we used lots of UML. But since some of the universities are no longer teaching UML, there are lots of people emerging from university and they've never seen UML. So that's kind of contributing to this mess. This guy here, he's got a very funny kind of video channel on YouTube. And when he was talking about modeling and UML, he basically described it as a very elaborate waste of time, which is kind of funny, but also quite tragic. So, what's his recommendation? And the answer is just use a whiteboard. And this is what I hear a lot from teams as well. It's like, yeah, we stopped using UML, and now we're just using whiteboards. The problem with saying things like this is we know how it ends up, because I've got 15 gigabytes of photos at home where people have just literally used a whiteboard. And this doesn't necessarily help us communicate the architecture of the thing that we're building. So in order to solve all these problems, we need to kind of step back and we need to say, who is interested in what we do? And there are lots and lots of different stakeholders, of course, and they all have very different levels of technical knowledge and also different things they want from our diagrams and documentation. So these are everything from software developers and architects through to scrum masters, product owners, business sponsors, lots and lots of different types of people. So the primary use of documentation, of course, is for communication and learning. So here is what we have built. This is how it works. And this is great for new joiners to teams, of course. There's another secondary use that we're not going to talk about too much today, but that's really if you do have a set of diagrams that are connected to your code somehow, you can use them as a basis for doing architecture refactoring and just generally architecture improvement. So that's a really, really interesting use that we don't often think about. So of course, none of this is new. If we go back to the mid to late 1990s, this guy here, Philip Cruikshank, was quite influential at the time. He created something called the 4+1 view model of software architecture. And he says this, to describe software architecture, we use a model composed of multiple views or perspectives. So essentially, this is taking your software system and looking at it from different angles. This is what 4+1 looks like. So you have to remember the context here. This was capturing requirements as use cases. A use case had a bunch of scenarios flowing through it. And essentially, you would document all of your important scenarios from 4 different angles. There's a kind of logical, conceptual, functional view, a separate development view that maps to code somehow. Process view is really parallelism, concurrency, and the final one is infrastructure and deployment concerns. So that's one way to do this. Some friends of mine in London, Owen Woods and Nick Brzezinski, they have a great book about software architecture. And in that book, they talk about this thing, viewpoints and perspectives. And viewpoints and perspectives takes 4+1 and it builds upon it and it extends it. In doing so, Owen and Nick also changed some of the naming of the views because they thought their names better reflected the intent of those views. Every other architecture book you read, any other software architecture document template you see out there will do the same type of thing. They'll take something like 4+1 and they'll change it in a number of subtle ways. So we have a couple of issues now. Number one, if I ask you to create me a logical view of your architecture, what does that actually mean? More fundamentally though, why is there a separation between the logical view and the development view? So this is something you'll see in common across all of the different ways of describing architecture. On the one hand, you've got this kind of high-level, fluffy, logical, conceptual, functional view of your system. And on the other hand, you've got something that hopefully maps the code. Do these two views of the system meet in the middle somewhere? The answer is normally no. And I get people saying this a lot. So whenever I visit organizations, they often show me these really grand-looking architecture diagrams. And then you ask the team, so are these useful? Do you use them? And they say, not really, because they don't reflect the code. Has anybody seen this? Yeah, so this is a big problem that we have in our industry. Another friend of mine, George Fairbanks, he has another great book about software architecture if you're really interested. In his book, he talks about the model code gap. So the model code gap is, imagine we are sitting around a whiteboard or a desk and we're having an architecture discussion. During that architecture discussion, we are going to be using words like service, maybe microservice, component, subsystem, module, layer. So these are architectural abstractions that we use when we're having a high-level discussion about a piece of software. Quick show of hands, who's a Java developer here? Right, so you're on your own. In Java, is there a layer keyword? Not the last time I looked. Any C# developers here? Oh, more C# developers. So in C#, is there a component keyword? No, same thing. So that's weird, isn't it? We're having this architecture discussion using component, module, layer, service, but the languages we use don't have these same constructs. So this begs the question, how do we create layers in something like Java? Well, what we do is we use packages, maybe. So what we're doing is we're taking packages, namespaces, interfaces, classes, folders, and files. We're assembling these things that we have available in our languages, and we're calling these things modules or components or layers. That mapping is what this is all about. If it's not clear how you go from abstract concepts down to code, that's the model code gap. So this is where the architecture diagrams don't easily reflect the code. Again, none of this is new. So I found a paper from the mid-90s, and it basically says, if I ask you to draw me a picture of the system you're currently working on, you'll probably draw me a nice high-level picture. A few boxes and lines, maybe a database symbol, because that's how you think about your software. If I find some tooling to reverse engineer a diagram from your actual code base, I will not get that same picture you just drew me. The picture I will get is very, very low level, maybe showing me all the classes or interfaces or packages. So it's very low level, it's very precise, but it's not necessarily how we as developers want to think about our software. It's the model code gap thing again. In order to solve this problem, we need to step back even further. And one of the big issues we have is that we don't have a common vocabulary to describe architecture. Even now in 2018, I think this is still the case. So let me run a quick quiz by you. So what's this? This is going to require some participation. What's this picture of? It's a map of London, perfect. What's this blue line going through the middle? It's the River Thames. What is a river? Right, water, flowing water. So a moving body of water flows in one way or the other depending on topology or tidal movements. This is something we learned hopefully as children, and we can use this knowledge to go around the countryside and find more rivers. What is this? Right, it's a top-down floor plan for a bathroom. Now don't go shy on me. What is that? It's a toilet. What is a toilet? Come on. You do know, don't you? It's another flowing body of water, one way, ideally. Again, this is hopefully something we learned as kids, and we can use this knowledge to walk around the building and go find more toilets. Any electrical people here? Yeah, a little bit. So electrical circuits, there are a couple of ways to describe circuits. what's that zigzag thing there? It's a resistor, right? What is a resistor? Resist stuff. Reduces the flow of current between 2 points or something, I don't know. Again, we know what that thing is on the diagram. We know what it is in real life. If I had a box of electrical components here at the front with resistors and switches and LEDs and capacitors, do you think you could come to the front and look through the box and find a resistor? Right. And if you knew the color coding, you could tell me how strong that resistor was. What is that? Why are you laughing? This is our world. Can anybody tell me what type of diagram this is? That might be a simpler question. Right, it's a UML component diagram. That's exactly correct. So given this is a UML component diagram, what are each of the boxes? So a UML component diagram should show components. So each of these boxes with this funny little symbol should be a component. But what does that mean? What's a component? Anything, yeah, exactly, anything. A grouping of stuff, could be a bunch of classes, could be a whole subsystem. Some of these look like COTS packages, so off-the-shelf packages. Some of these things look like UIs. There's no real easy way to tell what these components actually map to in the code base. And this is fairly stereotypical of what I see when I look at especially component or logical architecture diagrams. The problem here is basically the word component. So if you look up the word component in a dictionary, it literally means part of something larger. So imagine we are building a software system which is comprised of a web application talking to a database. We could say that the web application is a component of the whole system. That works using that definition, doesn't it? We can also say that no, the logging component is a component of the web application. So we can use the same word to mean very different levels of hierarchy, abstraction, detail. And that's an issue because I've actually witnessed design discussions where people on the team have been talking and using the term component, but meaning very, very different things. So that's one of the problems I want to solve here. It's ubiquitous language. If anyone is familiar with DDD, domain-driven design, we're trying to create a ubiquitous language between us as technical people and the business people. So when I talk about a customer or an order, you know exactly what that thing means. The irony here is that we as software developers don't have our own ubiquitous language to describe architecture and our software. So that's where we're headed with this. So there are two things I want to talk about. Abstractions and notation, because both are important. I actually think abstractions are much more important. So imagine you're at the whiteboard and you're drawing a diagram, and you're drawing this diagram during an upfront design exercise. The question you should be asking yourself with this diagram is, does the diagram really reflect what we think we're going to build? So are we going to code it that way, essentially? And if, on the other hand, you are drawing a diagram based upon an existing code base, the question's flipped. You know, does the diagram really reflect the actual implementation? Because if the things don't match, it's pointless drawing them. So my top tip here, and this sounds a bit weird, but bear with me for a few minutes. My top tip here is when you're drawing architecture diagrams, don't think like an architect, because that seems to get people in the wrong mindset. Think like a developer. And the reason I say this is because whenever I think about the architecture diagrams I've drawn in the past, the primary audience for these diagrams is actually other developers. Sure, some other architects want to know something about the software we're building, but fundamentally, these are diagrams for us as a development team. So that's where I'm coming from here. If you look at UML, UML tried to create a common set of abstractions and a common notation, boxes and lines, to represent those abstractions. Whenever I see people using UML, they're normally abusing UML. And a really good example is I'll often see teams drawing UML class diagrams, and a class diagram should contain classes that map to, say, Java classes or C# classes. A lot of the times you'll see a box in the middle, and it won't be a class, it'll be like a message bus or an external system or a database. And it turns out that people are just using a class diagram because it's a handy way to do boxes and lines. So they're kind of abusing both the modeling tool and the UML notation. So that's why I say this. I think the abstractions are much more important than a common notation today. If you look at electrical engineering, when I draw a zigzag, we all know that's a resistor. I think that might be a useful thing to get to in software, but we're not there yet. If this sounds foolish, next time you go back home, go and get 2 maps of your local area and lay them out side by side. The 2 maps of your local area will probably show you the same things, won't they? The same abstractions. The town centre, the city centre, the churches, the schools, the forests, the woods, the rivers, the bus lines, the metro lines, and so on. So they might show the same things, but they might use a very different colour coding, set of line styles, symbols, icons, and so on. So same notations, different, same abstractions, different notations. How do we decipher a real-world map? There's a key in the corner. So a real-world map is a really nice, simple example of a self-describing piece of documentation. It has all the information you need to, figure out what that thing is trying to tell you. So this begs the question, well, how do I do this? So when I'm thinking about describing a software system, for me, a software system is made up of 1 or more containers. Now, forget Docker for a moment. It's kind of unfortunate Docker became popular. What I mean by container is a separately runnable, deployable thing, something running in its own process space. There are a number of exceptions to this kind of guideline, but it's basically something that needs to be running for your system to function as a whole. In real terms, it's something like a mobile app running on a mobile device, a server-side web app written in ASP.NET MVC or Ruby on Rails or whatever, a console app, a batch process, a database schema, a file system, something like that. So if we look inside the containers, I'm going to say they are made up of components. So I want to use the word component to mean a grouping of related functionality, hopefully behind a nice, clean, simple interface. And components run inside a runtime environment, a container. Because I mostly deal with Java, occasionally C#, my components are ultimately built from classes. So basically, a component is built up from 1 or more code elements. Classes, interfaces, functions, objects, depends on the language that you're using, essentially. So that's a really simple hierarchy to describe the static structure of most software systems. Once you have this sort of thing in mind, you can then draw some pictures. So now we get to the C4 part of this. So the C4 model stands for context, containers, components, and code. And basically what we're doing here is we're drawing a diagram at each level in that hierarchy. I'm going to go through this very, very quickly today, but if you want more information, more examples, more links to tooling and tips and that sort of thing, go to c4model.com. There's lots of stuff on there. So the diagrams, you start with the system context diagram. And this basically describes the thing you are building and how it fits into the environment around it. So the system's context, and I'll show you some examples shortly. You then zoom in to the system boundary, and you show the containers inside it. So this is the mobile app talking to the web app, talking to the database, for example. You then zoom into one of the containers, like the mobile app, and you show the components inside it. And then you probably stop. So although C4 has 4 in the name, you don't necessarily go down to this 4th level. So if you want to show component implementation details, you can, but I definitely wouldn't recommend going down to this level, especially hand drawing this level. It's also worth bearing in mind that if you're building a microservice-based architecture where all of your services are very, very small, don't do this level either. Because once you open up your microservice, there might be nothing interesting inside it, so stop at level 2. So again, you kind of use this as a framework, and you apply some thinking to say when is enough detail. And it's diagrams as maps. So the reason I did the zoom in thing at the start with Jersey is because I wanted to plant that little seed. So sometimes, depending on who we're speaking to, we want a very high-level view of our system. And sometimes, depending on who we're speaking to, developers, other architects, maintenance staff, operations staff, we want to zoom in and show more detail. So this is essentially a set of diagrams that are like maps on top of a code base at different levels of abstraction, different levels of detail. So I'm going to give you a quick example. And this is for a kind of simplified internet banking system. So this is an example system context diagram. So imagine we are working for a bank and we are building an internet banking system. And our internet banking system is only servicing our personal banking customers. So what I've done here is I've got a box in the middle. That's my internet banking system. That's the thing we are building. I've identified my user type. So in this case, it's a personal banking customer. If you had more different types of users, you'd show them as, again, boxes on the diagram. And maybe our internet banking system is talking to the bank's mainframe back-end banking system. That's where all of the information about accounts and transactions reside. So maybe there's an interface into that banking system. And maybe we're using the bank's email system to send emails to our users. So again, this is slightly simplified in a real-world example. This context diagram would show many, many more integration points, but hopefully that's enough to kind of get the point. So that's the context. Imagine we want more detail. So how is this thing built? What we do is we take this middle box and we pinch to zoom in. So now we get to level 2. So this is the container diagram for the internet banking system. Now this is a bit more complicated because I want to talk through a number of things quickly. So this dashed box here represents the dark blue box in the previous diagram. So this is the internet banking system boundary. And what I'm showing you here are the containers that make up the internet banking system. So very simply, our customers can use either a mobile app on their mobile device to access information about their accounts, or they can use a web browser, so a separate single page application, maybe written in Angular. The single page application is actually being served from a server-side web application. So one of the things I want to do here is I want to basically point out that, so imagine you're building a server-side application written in C# or Java or Ruby on Rails. When you bundle up that application, you also tend to bundle up the client-side code as well, don't you? So you've got all of your Ruby on Rails code, all of your Java code, and all of your JavaScript code, your Angular code. So that's your deployable unit. You stick that on a web server somewhere. When people hit your web server, when they request pages, the server-side code might generate some content, and it might also send back the JavaScript. That JavaScript is then executed on the client side. So you've got a bunch of JavaScript code executing and a bunch of server-side code executing, and they're totally separate. They're separate processor spaces. So that's why I'm going to treat them as separate containers here. In order for these, the single-page app to talk to my back-end web application, there needs to be some sort of remoting going on, inter-process communication, maybe JSON over HTTPS. So maybe there's a separate API application as well, which provides a nice kind of JSON REST-style API for our mobile app and our single-page app. And maybe our API application is talking to some sort of database schema. So that's a simple example of a container diagram. It's just worth pointing out that this diagram does not tell you anything about clustering, scaling, sharding, availability, primary, secondary, failover, all that sort of stuff. So all of those sorts of things you save for a separate deployment diagram. So this is just the logical set of containers that make up the system. So this is good. We zoom into the API application. Now we get to level 3. So this is a component diagram, or a simplified components diagram, for the API application. Same thing. So this dashed box represents the API application, and the lighter blue boxes represent the components inside that API application. So the single page app and the mobile app both use a sign-in controller maybe, and an accounts summary controller, and there's a couple of other components here in the background. This mainframe banking system facade component, maybe that's the component we've built that's talking to our back-end mainframe system. So maybe we zoom into that thing, and now we get to level 4. So this is an example UML class diagram to show you the implementation details of that mainframe banking system facade component. And this is kind of where we start to get back to the model gap thing, the model code gap thing. So in order to jump from that box there into a collection of classes in the code, the model code gap needs to be as small as possible. So I do want some real traceability between the component level and the code level. So that's a quick run through of the C4 diagrams. And again, you can find some more examples online and so on. I also want to talk about notation, because notation is really important, but I don't think it's as important as the abstractions. Some tips. Put titles on pictures. Like, nobody ever does this. Even when you tell them to put titles on pictures, they literally don't do it. You have to go and beat them with a stick. No, you don't. So when I'm titling my diagrams, what I'll try to do is I'll try to say what the diagram type is. So this is a system context diagram for, and then the scope, internet banking system, financial risk system. So I want to be very specific and explicit about my diagram titles, because then readers know what to expect. Definitely be aware of using acronyms on your diagrams. If you're sure you are targeting other technology people, you can probably get away with the tech acronyms like JMS and JWC and all that stuff. Be careful of business and domain acronyms, the sorts of things that only people in your organization know about, because if a new joiner comes in and joins your team, now they're stuck. They have to go and ask what these acronyms mean. When I'm drawing my diagrams, I'll start with just boring boxes, and my boring boxes will have a bunch of text inside them. Now, if we think back to the abstractions, my diagrams are either showing software systems, containers, components, and people who use all of these things. So these are the 4 types of abstractions that I'm going to show in my diagrams. Each of my boxes will have a name, so I'm going to name all of my boxes. And I also want to be very specific about the type of these things. So I want to remove any ambiguity from the diagrams. You know, this is a person or this is a container. For containers and components, I want to be even more explicit and talk about some of the tech details. So this is especially relevant when you're doing upfront design, because technology choices are a part of the design process, of course. And also when you're retrospectively drawing diagrams, you have those technology information to hand, put them on a diagram. I will also include text that is really a description of that box, a description of that element. This is normally a single sentence, or it's a set of bullet points. And the reason I do this is very simply that. So the diagram on the left here is what people typically draw when they draw an architecture diagram. It's just a bunch of named boxes. So look, we have a content updater. What does it do? Well, it updates content, I guess. But naming is hard, so maybe we named that thing incorrectly. What I'm going to do is I'm going to add much more text to my diagrams, because now we can see, even if the name is wrong, we can read the text, hopefully, and get a feel for what that thing is doing, you know, what the responsibilities are. So that's one of my key tips here, put more text on diagrams. We should talk about lines, because lines glue your boxes together. Lines are really, really important, and I will typically favor one-way lines, so unidirectional relationships, one-way arrows. And this raises the interesting question, well, what do you show? Are you showing dependencies or are you showing data flow? It's entirely up to you. I tend to prefer the using, calling, depends on style relationship. So I will typically write something like the one at the top. So in this case, the trade data system sends trade data to the financial risk system. For me, that's much more explicit and precise. You could also say that the trade data system, arrow trade data, financial risk system. So this bottom one is typically what people draw when they describe data flow. And this can be a bit ambiguous, so I prefer to do the top one, but it's entirely up to you. Just make sure the text on the arrow accurately describes what you're trying to do here. And a good tip here is just read your diagrams out loud. So literally just read out, web application reads from and writes to database. You know, if that makes sense as a sentence, you're in a good place. So just read the diagrams, make sure your lines and the interactions make sense. Definitely add a key or a legends to all diagrams. You know, if you've got shapes or colors or different sized boxes or different types of borders or arrowheads, make sure you have a key or a legend to describe all of this stuff. Even if the color coding seems obvious to you. Because what happens is it seems obvious to you now, and then in 2 weeks' time you come back and like, green versus blue, no idea. It made sense, then it doesn't anymore. Yeah. That one. Yeah, yeah. So what a lot of people do is they'll have 2 boxes and they'll have a line with arrowheads both sides. Now, of course, most relationships are bidirectional. So if I'm a user using an application, especially something like a web application, I'm going to make a request, that's one arrow, and it's going to send me a response back, so that's a bidirectional relationship. What I really want to do on my diagrams is I want to try and summarize the most important intent or direction of that relationship. So in other words, rather than saying a user, I make a request and I get a response back, I'm just going to say the user uses the application. Similarly with this thing, the web application is reading from and writing to the database. So that, writing the text in this way allows me to describe that whole set of interactions with a single arrow, which hopefully makes this much more simpler. This is one of those things that you need to do. If you draw a picture and it doesn't make sense, or people ask you lots of questions about specific relationships, then use that as a feedback and say, right, how can we make this easy to understand? And maybe we do break this up into 2 arrows, reads from and writes to as 2 separate arrows. So there are no hard and fast rules here. It's kind of entirely up to you, but this is typically what I tend to do because it makes things a little bit simpler. So yeah, definitely have a key or a legend. Even if you are using UML, and I know there's only 1.5 people here using UML, but even if you do ever use UML, I'd recommend having a key or a legend on a UML diagram, because most people don't speak UML anymore. Same with Archimate, same with SysML. And keys and legends, yeah, they just describe colors and shapes and line styles and this sort of thing. So this is the key or the legend for my internet banking system container example. So you can see we've got some different colors here, some different shapes and so on. What I'll try to do is I'll use shape and color to complement a diagram that already makes sense. So if you look at a diagram and you take away all of the color and all of the shapes, the diagram should still make sense, because you've got the text in the boxes. And I'll add color and shapes to make the diagrams look prettier, to make them more aesthetically pleasing, or just to add an additional layer of information on top. But fundamentally, I think that shape and color should complement a diagram that already makes sense on its own. Which one do you prefer here? The diagram on the left or the diagram on the right? Yeah, right. So these two diagrams fundamentally have the same information on. That information is present in the text, which you can't read because this is so small. But most people tend to prefer the diagram on the right because it looks a bit nicer. And also, when you're standing back at a glance, you can see, oh, these look like people up here because they're people-shaped. And that might be a database because we've somehow associated cylinders with databases. And that thing looks like a folder. So when we're walking up to our diagram, we can start to already make some assumptions. So this kind of helps us get up to speed with the diagram more quickly. So what I'm trying to do here is I'm trying to increase the readability of diagrams so that they can stand alone. This is a contentious point in a lot of teams, but if you think about the typical life cycle for diagrams, someone creates them, they get stuck in a document, or they get stuck in a PowerPoint presentation. Somebody stands there and talks about the diagram during their PowerPoint presentation, and then that PowerPoint presentation ends up stuck on a wiki page somewhere. 2 years later, somebody joins the team, and they're told to look at the PowerPoint presentation because that has the diagrams on it that describe the architecture. They're flicking through the PowerPoint presentation, this makes no sense at all. If the diagram had more information on, more text about the intent, different levels of detail, it reduces the number of questions that new joiner is potentially going to have to ask you, because diagrams always end up floating around on their own. And any presentation you give on top of the diagram, again, should complement it. So once you have a good set of diagrams, you can then start telling stories on top of those diagrams. So this is how this feature works. This is why we made these design decisions, and so on and so on. There's lots of stuff I could talk about notation. If you want some more notation tips, if you go to c4model.com and scroll down, about halfway down, there's a PDF kind of checklist I created. And it's a simple kind of 2 or 3 page checklist that allows you to do a quick review of an architecture diagram. So, do you understand the boxes and the shapes and the color coding and all that sort of stuff? So that's available to download for free. So my kind of closing point of all this is abstractions first, notation second. When you take these ideas back to your team, make sure as a team you do have a good set of abstractions that you all understand, whether it's systems, containers, components, or something else. Make sure your team understands those abstractions, and then let your notations evolve naturally. I don't see much point in creating organizational-wide notation guidelines and standards for architecture diagrams, but make sure you have a key or a legend to make your diagrams as self-describing as possible. And that is that. Thank you very much. So we have 10 minutes if anyone has any burning questions. Yeah. Yes, so I didn't talk about tooling, so you can, because these diagrams are just boxes and lines, you can literally draw them in anything you want. Visio, PowerPoint, Keynote, OmniGraffle. So you've got a whole bunch of general purpose diagramming tools. I see a lot of people using tools like web sequence diagrams and plant UML. So something I didn't mention here is the C4 model is notation agnostic. So you can take the C4 concepts and apply them to UML. So once you've done that, you can use tools like plant UML. So basically write some text to get some diagrams. You've obviously got the modeling tools, star UML, rational tools, and so on. I have some tooling called Structurizer, which is a little bit different, and you may or may not like it. It's very opinionated. It only supports the C4 types of diagrams. And basically, and this sounds crazy, but go have a look if you're interested, you write your diagram definitions as code. So you're writing either Java or C# code to create a software architecture model which you can then export and visualize in a number of different ways. So built into, and these are open source libraries you can find online. There's a plant UML exporter, and there's an exporter for some other tools, but there's also an exporter for my structurizr.com web-based tooling. So you've got a whole bunch of options there. If you go to c4model.com, scroll right to the bottom, there are a bunch of tooling options, and people have built templates for draw.io and that sort of stuff. You're welcome. Any other questions? So how do I deal with the challenge of keeping diagrams synced with code? So this is a good question. This is basically why I built my structurizr tooling. So if I was to take any of your code bases, I could not create a good set of architecture diagrams on my own without asking you questions, because our code fundamentally does not include all of the information we need for these types of diagrams. So with my structurizr tooling, what I've done is I've basically, it's a simple kind of code-based DSL to create architecture models. You manually specify the top two levels, so the systems and the containers and their interactions. And then built into both libraries is a component finder. And what you do is you kind of run this little, so basically what you're doing is you're creating a console application. You're pointing this console application to your compiled Java or C# applications. And the component finder allows you to plug in different strategies to go and find components in your code base. So then you can use those to populate the diagram. So that's what I'm trying to do with tooling. I'm trying to automate as much of the lower level diagrams as I possibly can. That opens up a whole bunch of opportunities for you. The other way to do it is just to, if you have a definition of done for your work items, every time someone completes a story or whatever, you have a line at the bottom, have you updated the diagrams and the documentation? So again, you can just revert back to process. And then it's a very simple, hopefully small delta to an existing diagram, assuming you have an existing diagram, of course. So yeah, a bunch of different options there.